Welcome! Today we're going to unpack the blueprint for a tool that could quite literally save lives. And we're tackling a huge question that, every data scientist faces. You've got a bunch of different models, but how in the world do you pick the right one for the job?
So let's start with the big idea that's driving this whole thing. Can we actually use data to spot a crisis, like diabetes, before it becomes a full-blown emergency?
And make no mistake, the stakes here are incredibly high. We are facing a massive challenge where catching this disease late means much more severe complications and way more intense, expensive treatments for everyone.
So that's the mission, to build a blueprint. The whole idea is to shift the strategy from just reacting to problems to actually getting out ahead of them, being proactive.
This slide just lays it out perfectly. On the left, that's the old way, right? You wait for someone to get sick and then you react. But on the right, that's the goal. Using data to build a shield, to flag that risk early and maybe prevent the crisis from ever happening in the first place.
Now, to build this blueprint, we have to define what success even looks like. You've got business success, that's the real-world stuff like fewer ER visits. Then you've got analytics success, that's our technical metrics. And here is the absolute key insight. Those two things have to be connected. The clinic told us flat out, our business goal is to catch at least 80% of high-risk patients. So, our analytic goal just became finding a model with a really high recall score. That link is everything.
Okay, let's dive into the investigation. We're going to treat our patient data kind of like a crime scene, and all these health metrics, well, those are our clues. Our job is to figure out which ones are the real smoking guns.
So here's our case file. We've got health records for 768 patients. And for each person, we have these 8 clues to start with. Some are pretty straightforward, like age and BMI. Others are more clinical, like glucose and insulin. But the big question is, are they all equally important? And right away, our investigation hits a pretty big snag. Almost half the records for insulin are just empty. It's a blank. So what does that mean? Well, insulin could be a star witness, a really powerful clue. But if it refuses to talk almost half the time, it becomes kind of powerful, but also super unreliable.
So, after we run the numbers through a bunch of different tests, the results come in. And the first thing that just leaps off the page is how one clue is consistently at the top of the list. Every single time, glucose is number one.
The evidence is just overwhelming. We've found our prime suspect. Sure, other things like BMI and age are solid predictors, but glucose, it stands head and shoulders above everything else. This is the absolute cornerstone of any model we're going to build. All right, now that we have our clues, it's time to bring in our first lineup of detectives. We've got 3 common models, and we're just testing them straight out of the box. No special tuning yet. This is just to get a baseline.
Before we look at the results, we have to talk about this classic tug-of-war in any investigation. On one hand, you've got precision. That's about being right and not having a lot of false alarms. On the other hand, you've got recall. That's all about finding every single person who actually has the condition. You can't always have both.
And boom, check out the results. You can see this trade-off perfectly. Logistic regression is super precise. When it flags someone, it's usually right. But look over at that recall column. Naive Bayes is catching almost 70% of the actual diabetic patients. That's the highest of the 3. So there it is, our first big choice. Do we want the most accurate flags, or do we want to find the most sick people? And this brings us right back to the clinic's mission. When they were faced with that choice, precision or recall, they gave us a non-negotiable target. They said, we must correctly identify at least 80% of the patients who actually have diabetes. Why? Because for them, missing a positive case is way, way more dangerous than a false alarm. So this one number, this 80%, it's now our guiding star for every decision we make from here on out.
Okay, so those first results, they're a decent starting point, but to hit that 80% recall goal, we know we can do better. So now, it's time to roll up our sleeves and really get into the craft of tuning the model. This is where we unlock its true potential. We're going to focus on a decision tree for a minute, because in a high-stakes field like medicine, you have to solve what's called the black box problem. Think about it. If a model tells a doctor a patient is high risk, that doctor has to act. But if they can't see why the model made that call, how can they possibly trust it? Trust requires understanding. End of story. So a decision tree is basically just a flowchart of if-then questions. And the cool part is, we can actually shape how it works using these 4 crucial tuning knobs. Think of them like controls on a soundboard. We can set rules about how big groups have to be. We can limit how many questions it's allowed to ask.
and we can tell it exactly when to stop. This gives us direct, transparent control over the whole thing. Now this is where it gets really interesting. By combining these settings in different ways, we can create different personalities for our model. If the number one goal is making it easy for doctors to understand, we use more restrictive settings to create an interpretable profile. But if our top priority is finding every single positive case, we use looser, recall-friendly settings that let the tree dig a lot deeper.
And we can even take this a step further. You see, a single tree is awesome for clarity, but sometimes it can be a little unstable. So what's the solution? Well, instead of just one tree, let's build a whole forest of them. By getting hundreds of trees to look at the problem from slightly different angles, the combined result, the wisdom of the crowd, it ends up being way more accurate and a heck of a lot more stable.
Okay, this is it, the moment of truth. We've tuned our tree, we've built our forest. Let's bring all the contenders back for one final showdown and see which tool is really the right one for this job.
Okay, let's look at the final numbers. I added a column here called MCC. Just think of it as an overall balanced score. It takes both false alarms and missed cases into account. A higher score is better. And would you look at that? Naive Bayes still finds a few more cases, sure, but our random forest model has a much higher MCC score. That tells us it has the best, most reliable, most balanced performance overall.
And this really gets to the key lesson of this whole project. There is no single best model. It completely depends on what the clinic needs to do. If you need raw screening power to find every possible case, this guide shows Naive Bayes is your champ. If you have to minimize false alarms, logistic regression is the way to go. If the doctors need simple, clear rules they can actually explain to a patient, a tuned decision tree is perfect. And for a strong, reliable, balanced model for general use, Random Forest is the clear winner.
And I absolutely love this, because it shows how all this complicated data science work can translate into something so practical. The final thing the doctors get isn't some complex algorithm, it's a simple scorecard. A one-pager that just says, if the patient's risk is X, then you do Y. It turns a prediction into a decision.
And this leaves us with one last thing to chew on. As these models get more and more powerful, we really have to ask ourselves, what's more valuable? Is it just getting the best possible prediction spit out by some black box we don't understand? Or is it getting the best explanation, one that allows us to build a tool we can really truly trust? Because in fields that affect people's lives, sometimes that explanation is worth everything.